Good morning everyone. My name is Sirmuva from CSIT. Now I would like to present on the topic data normalization effects on neural network performance from the subject artificial neural network. Firstly, what is data normalization? Data normalization is a crucial pre-processing step in training neural networks. It involves scaling input data to specific range or distribution, usually to ensure that all features contribute equally to the model's learning process. Without normalization, some features might dominate others due to difference in scale, uh, leading to poor model performance, slow convergence, or even failure to train. In neural network, which use gradient-based optimization, normalization data helps the model learn faster and more accurately. Next, what is data normalization? Normalization transforms data into standard format or range. Commonly used techniques are min-max scaling, Z-score normalization, and robust scaling. Next, why data normalization matters in neural networks. In the world of neural networks, data normalization is not just best practice, it is a necessity. Without it, neural networks can exhibit unstable training behaviors, leading to challenges like exploding or vanishing gradients. These issues make it incredibly difficult for the model to learn effectively. Imagine trying to train a model where one feature's values are in the millions while another's are in single digits. The feature with larger values can dominate the learning process, causing the model to prioritize it unfairly, thereby hurting overall accuracy. Normalization ensures all inputs are on a similar scale. Next. Some common normalization techniques are uh, min-max scaling, Z-score standardization, batch normalization, layer normalization. First, let's see what is min-max scaling. Rescales features to a fixed range, typically between the range of 0 to 1. This method is effectively for preserving the relative relationships between data points, making it suitable when the data's original distribution is not Gaussian. Next, what is Z-score standardization? Transforms data to have a mean of 0 and a standard deviation of 1. Ideal for data that follows a Gaussian like distribution, it handles outliers better than min max scaling. Next, let's see what is batch normalization. Normalization activations within each mini batch during training. It helps stabilize training, allows for higher learning rates, and acts as a regularizer, reducing the need for dropout in some cases. Next, what is layer normalization? Um, Normalizes activations across the features within each individual sample. This technique is particularly beneficial for recurrent neural networks and transformer models where batch statistics can vary. Now let's see clearly about batch normalization, uh, which stabilizes the deep networks. Let's try to understand it better with the picture, which is over here on the left. Batch normalization is a powerful technique that normalizes the activations of a layer to have zero mean and unit variance for each mini batch. This process significantly reduces what's known as internal covariate shift, which is the change in the distribution of network activations due to the changing parameters of the preceding layers. By mitigating this shift, BN accelerates the training convergence of deep neural network, allowing practitioners to use higher learning rates. It has become a cornerstone in many state of the art CNN architectures like ResNet and generative adversarial networks GANs, leading to improved generalization capabilities. However, BN is sensitive to small batch sizes and adds some computational overhead during training. Next, let's see what is layer normalization, the RNN and transformer alien. And as a picture at the right clearly shows what is input layer, what are hidden layer, what is output layer. Input layer includes one neuron per component. Hidden layer has random neurons per layer. Output layer has one neuron per possible output. Yeah. What is layer normalization? The RNN and transformer alpha. Layer normalization offers an alternative approach to normalizing activations, especially beneficial for sequence models, unlike batch normalization. Layer normalization normalizes the activations across the features within each individual training example rather than across a batch. This characteristic makes it highly effective for recurrent neural networks and transformer models, where batch statistics might be unstable due to varying sequence lengths or when the batch size is very small. Layer normalization enables the use of high learning rates and reduces the model sensitivity to initial weight configurations. It is an integral component of modern transformer architectures, playing a crucial role in the breakthroughs seen in natural language processing over recent years, allowing for robust and scaling model training. Next, let's see the impact on training stability and performance. First, enhanced stability. Normalized inputs prevents excessively large weight updates, which can cause training instability and lead to oscillations or divergence. This stabilization allows for a smoother optimization landscape. Next, for faster convergence. With scaled inputs, models can converge to optimal solutions much faster, avoiding getting trapped in suboptimal local minima. This significantly reduces training time and computational resources. Next, improved generalization. Normalization acts as a mild regularizer, uh, particularly batch normalization, which adds a small amount of noise to the activations. This can help reduce overfitting by making the model less sensitive to the exact values of individual training examples. Next, robustness and accuracy. Numerous empirical studies across diverse datasets and model architectures consistently demonstrate that normalization leads to improved accuracy and overall robustness of neural network models, making them more reliable in real world applications. Real world evidence of normalization in actions like financial forecasting. In stock market prediction, models using artificial neural networks with gradient descent, ANN-GD, and functional link, artificial neural networks with genetic algorithm showed significantly performance gains when input data was normalized, demonstrating its critical role in time series analysis. Next, natural language processing. Cutting edge NLP models such as BERT, which have revolutionized language understanding, rely heavily on layer normalization for stable and efficient training. This technique ensures consistent activation scales across variable length sequence, which is crucial for complex architectures. Next, some of the best practices for applying normalization are consistent application, method selection combined with regularization, monitor batch size. What is consistent application? Always use the same normalization parameters to transform both your training and testing data. Inconsistent application leads to data mismatch and poor model performance. Next, method selection. Choose your normalization method like min, max, z score, batch, or layer normalization based on your data distribution and your network architecture. Combine with regularization. Pair normalization with other regularization techniques like dropout and weight decay. Next, monitor batch size. If using batch normalization, closely monitor the impact of your batch size. Very small batches can lead to noisy estimates of mean and variance, degrading performance. Aim for a reasonably large batch size where possible. Next, common pitfalls and how to avoid them. Small batch size with batch normalization. Using very small batches with batch normalization can lead to inaccurate mean and variance estimates, which destabilizes training. Inconsistent inference normalization. A frequent error is forgetting to apply the exact same normalization parameters during model inference. Over normalization. When normalization is good, excessive scaling or inappropriate methods can sometimes remove meaningful variance from your data, hindering the model's ability to learn important distinctions. Next, ignoring normalization. The most fundamental pitfall is skipping normalization altogether. This leads to significantly slower training, unstable gradients, and ultimately suboptimal model performance. Next, I would like to conclude the topic. Normalize to optimize neural network success. Data normalization is a foundational and dispensable step for achieving stable, efficient, and high performing neural network training. By ensuring that input features are on a comparable scale, normalization mitigates issues like unstable gradients and allows models to coverage faster and more reliable. Proper normalization not only improves convergence speed but also enhances accuracy and generalization capabilities, making your models more robust in real world application. The key lies in selecting the right technique, whether it's min-max scaling, z-score standardization, batch normalization, or layer normalization, tailored to a specific characteristics of your data and the architecture of your neural network. Embrace normalization as a fundamental best practice to unlock your model's full potential and ensure its success. Thank you.